Okay. Yeah. So the second question was what is something that you can do with B plus trees that you cannot do in hash-based indexes? And yeah, that is range queries. That is, you can say, return to me all records in between A and B. So everybody that was born between these years, or, you know, all students' names that begin with John, or, you know, all locations within a certain distance of this point. You know, all records that have a distance so far away from whatever. Range queries. So when you're looking in the range of something. Go down to the bottom here. Okay. Good. So I want to say a couple more things about hash-based indexing, and then we'll be done with foundations and we can start going into theory. So again, a hash-based index is when you find record locations by making use of a hash function. A hash function has a few properties. It can take any kind of input that you like, and it will output a number in a range that you can define. So that's written in a sort of shorthand math way like this. You have some function, we'll call it f, such that the domain of this function, like its input, comes from a set x. This could be a set of emojis or a set of words or a set of numbers, and it outputs some number. And this number is pseudo-random. What that means for the purposes of this class is that here, number 2 and number 3, that inputs that are close, for example, John with a capital J and John with a lowercase j, can produce very different outputs. Not only can, but I mean, almost surely will. Also, outputs that have, inputs that are very far from one another could produce very similar hash values. It's just an accident, okay? That's what pseudo-random here means. That give me an input, and I'll randomly choose where, like, what output I'm going to give. Now that output, number 1 here, should always be the same. If I give John with a capital J, I should always get this number back. But the reason why I got this number, 346112, instead of another number, it's because it was random. That's the effect that it should have. Pseudo-random, like random. By the way, random and pseudo-random, it's not that difficult to understand what exactly the difference is, but the differences can be a little subtle. And so if you don't like the word pseudo-random, you can just replace it in your head with the word random, and you'll basically have the same understanding of what a pseudo-random function does. Okay. Now, why is this random? Why use a random function as opposed to something else? Like, why use something that's pseudo-random? The reason is because this function, for example, if we want a function where we give it a name of a person. So here's John. You know, he's one point in this domain. Here's John with a lowercase name. Okay, here is A, B, C, C, D, E, F, F, E, Z, Y, A, G, K, K, whatever, some kind of nonsense thing, okay? Now, this domain here is really big, okay? If it's the names of people who are 100 characters or less, then the size of this is 26 to the 100. Okay, it's a very big number. But maybe we don't want that big of a number for the hash function. It's just, it's too much, and it'll take up too much space. You know, like having such a large number for every single name is a waste. So instead, we could say, well, we'll give it a 10-digit number. Okay, so the size of the output is 10 to the 10. So you have 10 digits. Obviously, this number is much, much bigger than this number. The number of possible inputs is very large. The number of possible outputs is small. This is why, so this is one feature, because we want a function that can take any characters of 100, you know, names of 100 characters or less. Why? Because we don't know what names people have. We know that they're going to be made up of these letters, so let's just say it'll accept any possible name. Now, so this set on the left is the set of all possible combinations of letters that are 100 characters or less. Most of these are going to be trash. What I mean by trash is that they're going to be ones like this, right? That's not a name that you're ever actually going to see. It's a combination of letters that could happen, but this isn't like a name that people are going to use. Instead, inside of here, actually I'm going to move this little John here. John. Out of the set of all possible names, the set of real names, these are names that actually exist in the world. Names actually used by people on Earth. Okay? The world has like 8 billion people. If everybody had a unique name, if everybody had a different name, well then, you know, 8 billion could be the size of this, which is much, much smaller than 26 to the 100. Now, because this function needs to assign a number to every single point in this domain here on the left, right? You give it this name, John, with a capital J. This input should correspond to the number 346112. Okay, so this name, John, and now this has all of the numbers between 0000 all the way up to 999999. So when you give this function the name John, it produces it matches the element John in the set of all possible names to the element 346110 in the set of 10-digit numbers. Now, you want to be able to have as many different numbers as possible. So when I give it names, I want very, very different numbers, because this way, this is sort of nice and evenly occupied. Okay? You don't want all of these numbers getting assigned to just a little tiny thing here. That would be bad, because you're having too many names that are giving you the same number. And if it's the same number, that's a problem, and I'll talk about why. That's called a collision. And you want to minimize collisions. So a good way to minimize collisions, to minimize two things ending up with the same number, is to say for everything, I'm going to give it a random number. And by giving it a random number, then sometimes it should be very well covered, this set. Okay, any number can appear with about the same frequency. So the way to do this, or a good way to do it, is to use randomness. Okay, that's why hash functions use randomness. When two functions are assigned the same number, that is a collision, like here. That's an example of a collision. I give the function two different things and I get the same number back. That's a bad thing, and you want it to happen not very often. Now, it will happen. In fact, it happens most of the time, because the domain is so big compared to the range that, of course, it's a pigeonhole principle, right? If I have 10 holes, 10 boxes, and 11 pigeons, some box is going to have 2 pigeons. Can't get around it. I only have 10 boxes, but I have 11 pigeons, and so I can try to spread it out as much as I can, but at the end of the day, at least one box is going to have 2 pigeons. Okay, that's called the pigeonhole principle, and it's the same thing here. I only have 10 to the 10 different numbers, but I have 26 to the 100 pigeons. So if I have 10 to the 10 boxes and 26 to the 100 pigeons, I can try to spread them out and put, only one in each box. But at some point, I'm going to have to start doubling up, tripling up, quadrupling up. Each time you have more than one pigeon in a box, that is called a collision. Okay, about this sort of high-level idea, are there any questions about this? No. Okay. Right, so this is where I left off, I think, the last class, saying the same point. You have this very large domain, you have a very small range. This little red circle here are names that exist in the real world. So long collisions there on the small set, on the small red circle, so long that's rare, this is called a collision-resistant hash function. Okay, so it's a little weird to call it collision resistant because collisions happen so much over the whole domain. But for the little tiny part of the domain that you'll actually be experiencing, if it's rare for that set, for the little tiny set here, then it's called collision resistant because collisions are rare for that little, for this little tiny part. Okay. So the way that this is used in databases, oh, come on. It's frozen. Okay. So the way that this is used in databases is you have a hash function. Why? Okay. F. And let's say I give it the name John. Now this is going to produce a number. So some number. And then we're going to have an index file with buckets. So this number is actually a number to a bucket. E.g. 3. So here, if I have bucket 0, 1, 2, 3, okay, each of these are buckets. And this bucket will be made up of two things. It will have, for example, let's see, bucket 3 here. This should have a record pointer. Record pointer to John in database. Okay, so the same way that B+ trees had record pointers, these buckets also have record pointers. Now let's say that we get another, and so I don't know, we'll have a bunch of buckets. These are all possible outputs of the hash function, i.e. the range. Okay? So we want a small, we want a range that's big enough where there's not so many collisions, but small enough to where we're not wasting a bunch of space with a bunch of buckets that are never going to get filled. Okay. Now, if there's, well, just for fun, yeah. Let's say that there's, I don't know, another one. Jenny Pinkerton. Whatever. Let's say that this also produces the number 3 by accident. Okay, this is a collision. A collision. This was an accident. Now, accident here, I don't mean an accident like you did something wrong and you need to fix it. I mean, this is an accident, like a coincidence, okay? This function should be returning random numbers. Sometimes it will produce the same random number for two different inputs. So then you can have a chain here. And now this would be a record pointer for Jenny Pinkerton. Okay, so you can have this sort of linked list to handle collisions. Oh, the hash function. So here, for the first level boxes, if the record is in here, then search is order 1. Remember that a B plus tree, it's O log of n. But a hash can be order 1, which basically means instantly. I mean, you instantly get the thing. If it's in this first level of buckets. If, yeah. Why is it order 1? Okay, well, we want to find the record for John. So we give this to the hash function. The hash function gives us the number 3, okay? Then we go to bucket 3, and then, there's John's record pointer, we found it. Okay, so it's a constant number. It's like 1 or 2 steps, always. It doesn't depend on the length of John or the number of anything. It's just, takes 1 or 2 steps and you're done. So that's order 1. If the records are in this first row. Now, when you have collisions, then it might take longer, because if you have lots of collisions and then you have this list getting really long, this part of the list has no order. So you just sort of have to go through it one by one. Okay, so a hash-based index will have a hash function and an index file, these two things. The index file is this set of buckets. For a B plus tree, the index file is the structure of the tree itself. So you can take the index file and construct the B plus tree. Here, it is an encoding of a bucket number and then record pointer. Maybe you have multiple record pointers if you have a chain like this. Okay, so hash functions can only do equality searches. So find me exactly the name John with a capital J. Not John with a capital J and some last name. Give me all of those Johns. Doesn't work in hash-based indexing. You can only search one by one. So you can do equality searches. Less than, greater than, this concept doesn't exist for hash functions. Here when I'm using names, it happens to, but a hash function should be able to work for anything. Emojis, sound, I don't know, things with no natural ordering. A hash function can work on anything, and which is why you use it essentially because you have to. If you have the choice, it seems a B plus tree is usually a better way to go, just because you can do range queries, which is Good. Useful, helpful. Okay, any questions? It's making me uncomfortable that there's 37 people here and no questions. Can I talk more about the chain? Yeah. Okay. So here's our file of records. Okay, this is the large, gigantic, unordered raw data. In any case, it's the raw data. Unordered, arguable, but it can be unordered. You can also order it, maybe, if you want. There's some benefits to doing it. But the important thing is that this is the raw data. Okay, so this is the data with like a ton of columns. You know, here's name, age, address, salary, favorite food, favorite color, whatever. I mean, just on and on and on, like lots and lots and lots of data. That's the file of records. Now, the file of records, these are stored in blocks on the hard disk, right? So on the disk here, remember that you have sectors, which is like a pizza slice, and then you also have tracks, which are like circular things. This is called a block. Okay, a block on the disk. That's the smallest piece that the disk will return. Now, this is usually 512 bytes. Maybe it can be up to 4 kilobytes. You know, that level of detail doesn't exactly matter, but know that it's something like that, okay? Now, let's say, for example, this entry takes 128 bytes. Let me do that in a different color. Um, 128 bytes, okay, for a row. Okay, that means that if you're getting a file from the file of records that's on the disk, remember, then it will return to you a block. So this is, I don't know, let's call this block A, or block 1. I don't know, block 1. So here on block 1, there will be 4 entries. 2, 3, 4. Right? Why 4? Because it's 128. This is also 128. That's 128. That's 128. So in that single block, there's 4 records. 1, 2, 3, 4. Okay? Now, those records, the hard drive doesn't know that there's 4 records there. The hard drive only knows that it's returning a block, and so it's going to return the entire block. You can't break it down any further. Okay, so that's a block number. And now this table, the unordered raw data, block 2, and then 3, and on and on and on, okay? Lots and lots of blocks. Okay, these blocks are the indices. Okay, I'm writing block to make it more explicit. A block can have more than 1 record, every time you access the disk, it will return one block at the minimum. And, then not fractions of a block either. It'll return 1 block, 2 blocks, 5 blocks, 10 blocks. Not 1.5 or anything like this. If it needs 1.5, it'll round up to 2. Okay, so that is the location of the records on the actual disk itself. Okay, then you have an index file. So let's say this is block number. And now this is going to be indexed by whatever the range of the hash function is. So let's say the hash function goes from 0, 1, 2, 3, 4, 5, whatever. These are the range of hash function. Okay, all of the possible outputs of the hash function are here. I'll start with 1, whatever. And then there is going to be a block number, and let's see. Yeah. Okay. So I'm going to try to draw, I'm doing it a little differently here. I'm drawing it as a table instead of as blocks with arrows. Here, instead of the arrow, I'm just using the index number. And then here you have a hash function. Okay, and this takes, let's say, names and outputs a number. So here, if we give it John, maybe this output the number 4. Okay, then here in the index table, it will have, name, block number, name, block number, pointer to next bucket. Here I'm making the bucket sizes such that they can only hold 1 name. They might hold more, but in any case, like, you're going to run out after some fixed time, right? Maybe you can fit 5 or 10 or whatever. I'm just going to use 1 here so that each bucket can hold 1 name before it's full. So here we have the name John, and maybe he's in this row. Maybe this is John here. Okay, so then it'll have the block number, block 1, because that's the block that contains this entry for John. Now, so this takes time. Order 1. I want the record for John. How does that work with a hash-based index? Well, I give the name John to my hash function. It returns a bucket number. I go to the index file, and I look at that bucket, and I look to see the name John, and where is that record, which block is that on the disk? That's on block 1. And then the hard drive will spin up, and it will return back to me this whole block. Okay, so I'll get 4 entries back, but that's fine. It's constant numbers just don't really matter. So then I'd get a block back with 4 entries in it, and I search through it until I find the one for John, and then that's my record. Here you go. All right, so then I can return this whole thing, this John, that record. Okay, so that's the process for how we'd find John. Now, let's see what happens if there's a collision. Here's f of Susie. And that also gives the number 4. By accident, okay? This is a collision. This should not happen often. It's rare, but it does happen, and so you need to handle it, and this is how you handle it. So the block has records in the... Okay, hold on, I'll get back to that. Okay, so here's Susie. By accident, produces the same output for the hash function. So let's do the same thing we did for John and follow Susie. Right. So this is extra file. Overflow. I'll call it an overflow file. I don't know that this file actually has a specific name, but I'll call it an overflow file because things have now overflowed in the original index file. And now Susie, great, we want to follow this number 4. So then we go to this row 4 in the index file. But we see that John is not equal to Susie. So we should not follow this, right? Because that's for a different person, that record. So here we have a pointer to another file that now has name, block number, and another pointer to the next bucket, okay? So here, now this is Susie, and let's say that she's at block 18 and fine. So here, ... in block 18, we have 1, 2, 3, 4, and here is Susie. This is Susie's row in this block. Sorry. That's Susie's entry inside of this block number 18. So now when we go through this and we're looking for Susie, we give Susie to our hash function. We get the number 4. We follow 4 into the index file. We see that Susie is not equal to John. So we have to now follow this pointer to the overflow file and see Susie is equal to Susie. Her record is in block 18. So load up block 18 and return this whole block that includes the record for Susie. Look through the records that have been returned and find the one for Susie and return it. Now you'll see that, there's no way here. This is all unordered, all of this stuff here. Any output files, any of the other buckets, there's no order to them. And you'd be wasting time to try to order them because it should be rare. These chains should be fairly short because collisions should be rare. It's only in the case of a collision that you have this sort of chain. Okay. I see a question here. The block has the records and the outputs to the buckets. No, the blocks have the records. Yeah, blocks here, the blocks, this is something that exists on the hard drive, okay? Like this is like how the data is actually stored on the drive. And so those are blocks. They're indexed by block numbers. This index file here is, I mean, these are also indices, but they're not block numbers. They're not anything like that. It's a number that you can define for if you want your hash function to return numbers from 0 up to this number, and then you define whatever that number is. That's the maximum number of first level buckets. So you could use a very small number like 1. You can have a bucket size of 1, everything goes into the same bucket. That's a stupid thing to do because now, you know, it's a linear search. It breaks down into a linear search because there's no order on anything. You have to just start at the first one and then keep going down the chain until whatever. You could also have a gigantic number of buckets. Could do that, but this index file is as big as the number of buckets. So if you want to have 10 kajillion buckets, that'll be enough, but then your index file is going to be gigantic. And most of it that's just wasted space. So there's a trade-off. There's a sweet spot for how big you want your index file to be. That depends on things like the type of hardware that you're using, the length of each record pointer, the sizes of the block, the blocks, the sizes of the pages, whatever. Would this still take time N1? No. The time, and that's not N1, O1. The time where it's basically instant is the case when the record is in here, in this part of the index file, right? Because that's one hop. So you give the hash function your number, one hop, and if the answer is in this, I'm calling it the first bucket, then yeah, that's order 1. After that, it's hard to say. It depends on the number of collisions that have happened. Yeah, so there's no guarantee. Depending on the way that you define your hash function and stuff, maybe you could keep it order 1, but that's beyond the scope of this course. I mean, generally, the number of collisions are so few that a hash function is faster for equality searches. So if you just want to know if something is exactly equal to something else, then a hash function can be good because it can be faster than a B+ tree. But it cannot do range queries. So yeah, that's sort of the cost-benefit analysis that the database manager would have to decide on. You know, is our equality, maybe you have both. You know, maybe like you're doing a lot of each. You want the, I don't know. You know, it's up to you to design. Okay. Any more questions about the hash function? Somebody else asked me to compare the hash function and the B+ tree. So I'll do that again very quickly. And I'll just use the same example with John. Okay, so just step by step, how do we retrieve the record for John in a hash-based index? Actually, instead of me going through it, I'm going to pick out on a student to walk me through that. Let's pick on, how about Nicole?
Hi.
Oh, sorry, my volume's down. There we go.
Can you hear me?
Yeah, I can.
Awesome.
Okay, so Actually, let's do Susie, just because that way we can show what happens with the collision. So, yeah, just walk me through it. I give you the name Susie, and I want the record that that contains Susie.
So basically, the hash function would return number 4, which corresponds with the index file value. It would see 4 and it would recognize John in the name, but John is not equivalent to Susie. So it would not go to block 1. Instead, it would go to the pointer to the next bucket in that overflow file. It would recognize that Susie is in fact equal to Susie, and then go to the block number of 18 and search through until it finds that correct entire file of Susie.
Yeah.
Entry rather, Susie.
Very good. Yeah. Yep, just like that. Okay, excellent. Now, let me go up to the B plus tree. I had a better picture. Oh, actually, I think I did over to the side or something. Great. Let me pick on, how about Serena?
Yeah.
Okay. So I'm not using a specific, like a complete drawn out example. I'm going to use this sort of bigger kind of tree, this abstract one, and you can just sort of make up some things that are reasonable. Now, let's say that I want to find the record for John. And now here's the same thing, file of records. And here's John in block 1. Okay. How would I, now using a B plus tree, return this entry for John? When you're working with a tree, where do you start?
At the root.
At the root. Okay. So let's start here at the root, and I'll say that that is the name Mary.
Okay, so then you would check, I guess, whether John is either less than or greater than Mary, and then act accordingly. So John will be before Mary, so you would check the left child next.
Okay, great. So you check Mary, go to the left. Okay, and let's say that that is, I don't know, Lucy.
So then you do the same process. And then, so then, right, it's still going to be less than.
Okay.
And then,
and I'll just make it up. I mean, like, make up some path.
Yeah, sure. So then I guess you would just follow that until you reach John. So maybe let's just say, yeah, that works.
Sure.
And then once John's found, then it would just return, I guess, the location of the node within the array.
Yeah, so this would actually have, I mean, so remember the leaves in a B plus tree has the key, here John would be the key, block pointer, and maybe, you know, key 1, key 2, key 3, it depends on the degree. So I don't know, key D, block pointer. If this has like a degree 4, maybe there's 5 entries here. Each of these are different pointers into the block. And then, sorry, there's also a next leaf pointer. So whatever. Let's say that here, this is John, and this is 1. So this is a blown up leaf here. Okay, so now we found John, and what?
Oh, no, I didn't say anything.
Oh, yeah, so I'm asking you to just finish it up.
So it'd be John in block 1, and then I guess whatever pointer that is, whatever's pointing to John, and then or the leaf that contains John, and then the next entry after John.
Yeah, so that's, yeah, whatever. That's the block pointer. The number 1 here means that it's in block 1. So then you request for the hard drive, return to me block 1, and then it will return to you the entire block. Then you search through that block for John, and you're done.
Makes sense. Thanks.
Oh, makes sense.
That makes sense.
Okay, good. All right. Let's see, just some sanity checks. How about Jerry?
Hi, Professor.
Hey. So for this B+ tree, when we were finding John, we started at the root, and then, you know, we had to kind of burrow down all the way to a leaf before we could then pull the record. Could there be a case in a B+ tree, let's say Lucy, if I wanted Lucy's information? Could I just stop here and then jump directly to the file of records?
To the best of my knowledge, I think you still have to go down to the leaves.
Correct. Yes.
Okay.
Yeah, so the leaves are the only things that hold the record pointers. The record pointer here being this this pointer, you know, this pointer.
Okay.
Yeah, so because the internal nodes don't have any record pointers, you would still have to burrow down somewhere, and then here there would also be a Lucy. So she'd repeat. Okay, very good. Yeah, that was just a sanity check. Cool. Okay, so let's see, do you ever find collisions in a B+ tree? There's not really collisions. Yeah, there shouldn't be collisions. You would need to decide if you go left or right. Yeah, on this type of equality. That's up to you. Just be consistent. To the student who has an exam, yes, that's fine. Okay, well, this took a little longer than I was hoping. I was wanting to get to actually our diagrams today. But I guess because we've only got 4 minutes left, let's just, I don't know, I'll take time and answer any questions, or if you want like another example or anything like that, I can go through them. When will our midterm be? I mean, before spring break. I don't know the exact date yet, because I want to cover a certain amount of material before. So it'll probably be either after we're done covering ER diagrams, or just after we cover relational algebra. Can I do another B+ example? Sure. Let me go up and one with, because here I actually drew a full B+ tree. Sorry it's so messy, but I'm looking at this. Oh. This. that's actually a proper B plus tree. Okay, so here, these would be the blocks, block number. Okay, now for this B plus tree, maybe I want the entry that corresponds to student ID 15. Okay, so I start at the root. And I see that the number 15 lies in between the number 10 and 20. So I follow this path. Now I'm at this node, and I see that the number 15 exists in the node itself, and this is a leaf. So then I can follow this pointer to request the block to return back this entire row. Block number and index number interchangeably. It depends on which it depends on what table I'm talking about. For the file of records, or the heap file, those are block numbers. But they're also indices into the hard drive. So an index is a more broad term. Sometimes an index can be, an index can be whatever you want. It's just how you label the row is an index. Sometimes those labels have meaning, like here, the meaning in the heap file of the index is the block number. So once you get that index, you know exactly which block from the hard drive to request. Let's see. Okay, can I repeat the steps for the hash function example? Sure. Okay, here's our hash. Now we have three things here. We have a hash function. We have an index file. Oh, sorry, I'll go down to the one down here. That's better. We have a hash function. Let me erase these. And so 1, we have a hash function. 2, we have an index file. And then 3, we have the file of records. Okay. Here, the index, both of these tables, the index file and the file of records have indexes. Index numbers. But their meaning is different. The index numbers for the file of records correspond to a block number on the disk, on the hard drive. These index numbers on the index file, these are just sort of made up virtual numbers. They don't have any special meaning, except for they define the maximum size of the index file. I don't want the index file to be bigger than this number, so that's how many index values I'll have for the index file. Okay. So let's go through this. Let's find the record for John in a hash file. So somebody gives me the name John. I start at number 1 and I give it to the hash function. This hash function returns to me the number 4. So then in the index file, I go to the 4th entry and I see that here, John is the first record that I hit. And where is the actual record for John? It's in this, number 1. So now I follow this pointer and I get block 1. And then this returns the entire block. Now I have the block, and then I iterate through the block Looking at each entry, 1, 2, 3, 4, there's only going to be 4 of them. I happen to find John straight away, and then this is what I return, this whole record for John. What if John was in the second row? Yeah, okay. So if John's in the second row, John. So all the other steps are the same. John's at 4, go to the index file, look at number 1, it's in block 1. The hard drive returns this whole block, and then I just look through it for the entry for John. And now I find it, oh, here, in the second row. So now I just returned that one. Those 128 bytes. In this example, I was making each row 128 bytes. That would be 01, yes. It's guaranteed to be 01 if the number is in the first bucket. By the first bucket, I mean it's here. You know, you find the name in this in this index file, not any overflow. If there's lots and lots and lots of collisions, again, you could have an index of 1. I'm sorry, an output range of exactly 1. Every name gets assigned the same number. Then it's not order 1, that would have to be order n. So guarantees go away if it's not in the first bucket. Practically speaking, though, collisions are very rare, and you probably only have a constant number of them. So equality searches are generally still faster, being order 1 in practice, but the math breaks down, and you can't make that guarantee mathematically. You could say practically that's probably the case. What is the overflow again? The overflow is what happens when you have a collision. So here, for example, John and Susie generated the same number for the hash. But I can't, if I follow Susie now, oh no, a different one. So here now I'm looking for Susie. Susie's at number 4. I go to number 4. That's John. That's not Susie. I should not follow that and return block 1. Because that's where John is. That's not where Susie is. But the hash function told me to stick to this row of the index file. But because the index file has a fixed length, then this can go into an overflow file. And so it's a pointer that now you can go somewhere else on on disk and pull it up, and then that could create a chain. So in this example, this would be the first bucket, this would be the second bucket. If you have another one, f of smiley face, that also equals 4, then here you'd have to have another pointer to another file that would have the smiley face, and then its block number 42 and whatever. And so now if you're trying to find the smiley face, you'd start at the smiley face, go to the index file, follow this pointer to this overflow file, follow this pointer into the next overflow file, and depending on how many collisions you have, you could see that that could get rather long if you have a lot of collisions. But these hash functions are collision resistant, meaning that that should be rare. So the length of these chains should be small. When it searches block 1, does it search in order? Row 1, row 2? Yeah. Yep. So once you have a block, you do a linear search on it. But the block is of a constant size, so that linear search is still constant time. Blocks can be any size. No, blocks are defined based on the hardware of the hard drive. Typical block sizes are 512 bytes and 4 kilobytes. But for example, 1 megabyte, nope, doesn't exist on any hard drive. Like that's too large of a block size. It's a fixed thing that's based on the hardware of the hard drive itself. Are they always just 4 lines of records? Four blocks because of memory limitations. Yeah. So here in this example, I'm saying that the hard drive itself, so like this here, the disk, this part here, that's 1 block, and that's a hardware requirement. How many rows can you add to that block? It depends on the maximum size of the row. In this example, I was making the rows equal to 128 bytes. Therefore, 1 block can hold 4 rows. It could be also that maybe a block is 512 bytes, but each of your rows is a kilobyte. Now you need 2 blocks to hold a single row. Could be. I mean, that could happen. These are the kinds of details that yeah, you might be able to now think about, but I'm not going into all of them for this class. That's too much.
Hi, Professor. I have a question. So I was just trying to understand the kind of the differences between like a B plus tree and a hash-based index. So would you say that the hash-based indexing is much faster than a B plus tree, like in terms of locating the data?
Generally, yeah.
Okay.
Yeah.
Okay.
But it has limitations. Namely that it can only do equality searches. So no ranges. No, return to me the records of all of the Johns. You could only say return to me the record of John Smith, that exact one.
So like a specific one pretty much. Okay.
Right, yeah. Or return to me the employee that's earning $48,672. Not return to me all of the employees that are earning under $50,000. That would not work for a hash function.
Gotcha. All right. Thank you.
Mm-hmm. How does it work if 2 employees make the same amount? Well, let's see. In a hash-based index, that would not be allowed. That is to say, if 2 employees make the exact same amount, that you would have to give some other piece of information to identify them. Because that is, I mean, it's an interesting question, and there's basically no answer if the key values are not unique. And that's why in database systems, when you make an index, you define a primary key, and we'll talk more about this. But one of the features or one of the requirements of the primary key is that it has to be unique. No, you can't have 2 values of the same thing. So if you had, if you were making a key based on just the income, and 2 employees had the same income, you would get an error. Yeah, like you can't add this employee with that salary, one already exists. So you have to assign it a different salary. Otherwise, you could expand the number of keys. You wouldn't query on salary at a large company. No, you would. You would just use a B plus tree. I mean, I think that there's plenty of queries about salaries happening. I think that's probably a pretty common one. Yeah, you probably would not use a hash function. That's correct. Okay, great, you too.